Hey everyone, let's jump right into this explainer. Today, we're doing something really cool. We are going to reverse engineer the incredible, multi-stage journey of building a large language model. We'll literally trace the path from raw, chaotic text all the way up to a highly capable AI assistant. Now, if you've been following the AI space at all, you know things are moving at light speed. But understanding exactly how these engines are built, well, that gives you a completely different perspective on what they can actually achieve.
Just look at the sheer explosion of research on this graph. That hockey stick curve since 2018, it's absolutely wild. It proves just how fast the scientific community is racing to unlock human-level natural language processing. And notice how those blue bars, which represent base large language models, skyrocket? But don't ignore the red and green bars either. Those represent fine-tuning and alignment, proving that this whole field isn't just about making models bigger anymore, it's about making them smarter and, for sure, making them safer.
To really set the stakes for why this matters to us, we have to wrap our heads around the mind-blowing scale we're operating at here. We aren't just talking about your standard algorithms anymore. We are looking at gigantic architectures digesting massive chunks of human knowledge. Models like Palm scaled all the way up to 540 billion parameters. And multilingual models like MT5, they've learned to master over 100 distinct languages. It's like they're digital sponges just soaking up the entire internet.
So here's our roadmap for today. We're going to cover the research explosion, lay down the foundations of data and pre-training, peek under the hood at the architectures, and finally track fine-tuning, alignment, and the overall evolution of these models. Let's get to it.
Starting off with Section 1, the LLM research explosion, where we map the frontier.
Take a look at this taxonomy tree. It basically illustrates the master blueprint of our building process, splitting the massive LLM landscape into its essential branches. You can see exactly how the ecosystem is divided up into pre-training, fine-tuning, efficient tuning, inference, evaluation, applications, and challenges. So this isn't just some random collection of experiments, right? It's a highly structured, parallel effort happening across the globe to refine every single piece of the AI puzzle.
Moving right along to Section 2, Foundations. This is all about data and pre-training, the raw materials.
Okay, so the absolutely crucial point here is that before an AI can read anything, it has to translate our human language into something it can process. It literally slices our chaotic, messy human words into mathematical puzzle pieces called tokens. Now, whether it's characters, subwords using byte pair encoding, or whole words, these tokens are the fundamental raw materials. Because without clean, well-processed tokens, the entire language model, no matter how massive it is, just completely falls apart.
Which brings us to Section 3, Architectures. Let's look under the hood and see how this framework is actually constructed.
When researchers build the brain of these models, they specifically rely on the transformer architecture. And there are three primary ways they set this up. We've got the causal decoder, the non-causal or prefix decoder, and the full encoder-decoder setup. And the choice they make here? It depends entirely on how they want the model to look at past and future words to understand the context of what's being said.
If you ever wondered how the machine actually pays attention to text, this visual breaks down exactly what parts of a sentence the model is allowed to see. In a causal decoder, the model only looks at past tokens to predict the next one, kind of just like how we read, left to right. But in a non-causal or encoder-decoder setup, the attention can be bidirectional. That lets the model look ahead to gather deeper context before it makes a decision. It really is a brilliant piece of engineering.
And to strengthen that framework, the models go through some pretty rigorous testing with different training objectives. Think of this as sending the AI to grade school. We give it fill-in-the-blank exercises with masked language modeling or finish the sentence tasks with full language modeling. By forcing the AI to predict missing or future tokens billions of times, it slowly builds this shockingly accurate statistical map of human knowledge.
All right, Section 4, Fine-tuning. This is the specialization layer where the model learns to actually follow instructions.
Think about it like this. Pre-training gives the AI its massive vocabulary and its knowledge of the world, but it doesn't know how to talk to you yet. At that stage, it just wants to auto-complete text. Fine-tuning, and particularly instruction tuning, is what actually teaches it to follow your specific prompts, answer your questions, and act like a helpful chatbot. Without fine-tuning, you basically just have a really powerful auto-complete engine, but with it, you have a dedicated assistant.
Now for Section 5, Alignment, putting human values first to create a crucial safety layer.
You see, a smart AI isn't automatically a safe AI. To make sure the model stays helpful, honest, and harmless, what the industry calls the HHH criteria, researchers use a really complex three-step loop called RLHF,
or reinforcement learning from human feedback. First, they do supervised fine-tuning on good demonstrations. Then they build a reward model to rank how well the AI is doing. And finally, they use a reinforcement learning algorithm called PPO to optimize the AI's behavior based on those rewards. Following the flow on this diagram, you can see how human labelers actually score the AI's outputs. They're the ones deciding what's a good response and what's a bad one. That direct feedback trains a reward model, which then automatically guides the main LLM. It iteratively forces the model to align with human intentions. So it's essentially teaching the AI to prioritize safety and usefulness rather than just spitting out the most statistically likely word.
But here's the real takeaway. Alignment is an endless battle. Even highly trained models can be jailbroken, and that requires constant red teaming, which is where human testers intentionally try to break the model's rules just to expose its vulnerabilities. Once they find a weakness, they patch it. It's this continuous, ongoing loop of testing and refining.
And finally, Section 6, the evolution of LLMs. Let's look at the scale and what the future holds.
When we track these milestones, it becomes super clear that progress isn't just about blindly throwing more computers at the problem. Back in 2020, GPT-3 proved that huge models could do zero-shot tasks. By 2022, DeepMind's Chinchilla taught us how to scale those models efficiently, and jump to 2024, models like Llama 3 proved that highly capable, aligned models could be put directly into the hands of the open-source community.
This timeline right here perfectly captures the climax of our story. Look at the upper half, representing open-source models, and the bottom half representing closed-source corporate models. It's this fierce, ongoing competition. Every time a massive closed model makes a leap, the open-source community, fueled by efficient architectures and shared data, races to catch up. And that dynamic is driving the entire industry forward at breakneck speed.
And the secret sauce behind this rapid progress? Well, visually, we can see why the Chinchilla scaling law was such a game changer. If you double the size of the brain on the left, you absolutely have to double the amount of books on the right. Simply adding more parameters to make a model bigger is completely useless unless you equally feed it more high-quality data. That realization fundamentally changed how every major AI lab allocates their massive computing budgets today.
Which leaves us with a pretty thrilling provocation. We've seen how they tokenize our world, build structural attention spans, study human knowledge, and learn our values through feedback loops. So, now that we understand exactly how these AI engines are built, as the data scales and the architectures become even more efficient, what seemingly impossible tasks will they master in the years to come? The blueprint is clear, but the destination, well, that's entirely up to us.